Hello everyone, welcome to today's Math Club talk. Today with us we have Daibik Barik. He's a second year here at ISI Bangla, and his interests are in discrete mathematics, and he's going to give a talk on fuzzy set theory. Over to Daibik.
Thank you. Thank you for the introduction. So, I will be giving a talk on fuzzy set theory, and the prerequisites are basics of set theory, relations, and a bit of notions of supremum and infimum. And yeah, that's it. You can follow the talk. So last week, if I remember correctly, Avyakta gave a talk on set theory. This is kind of. So yeah. So firstly, what is fuzzy? So like if you say a sentence like I'm taking a very trivial example. So like if you want to give a gift to someone of say rupees 200, right? And you find a gift that is suitable for the person, but the price is 210. So we all would gift it, right? Because it's just 10 rupees a difference. But if you say it mathematically, our budget maximum was 200. But here we are exceeding the maximum because of certain conditions. So to see clearly, this our maximum wasn't 200, it was in a neighborhood of 200. Say it was from 190 to 210, or maybe 185 to 215. So in this case, 200, like if we define the set A, where A is x less than 200, this was what our defined set was for the budget. But then we made it such that x was less than 210, right? Or if you define it more rigorously, the maximum, like or the supremum of x, it was equal to 200, and the supremum now lies in 190 to 110. So if we take the membership of the function, like the supremum of A, this becomes a set which has its values from like right. So like the examples that given here are today's temperature is hot or the cake is sweet. So to think like it's hot, right? Okay, so what is the temperature? The temperature is greater than 30. So that is us assigning a perfect clear temperature which is greater than 30. But we don't know the actual temperature, right? It might be from 35, it might be 32, 33, it might be in a range from 30 to 35. So basically what I mean to say is, always the things that we think as crisp sets, they are not that crisp. They might be a range that we never talk about, but it is present there. So like the question is, are they mathematically rigorous? But again, mathematically rigorous is a fuzzy thought. Like what is rigorous? What do you mean by rigorous? So how rigorous are they? That is the point. So like kind of these are uncertainties, right? And we in mathematics, general mathematics, we use probability to deal with uncertainties. But in this case we are not doing so, because probability deals with the type of ambiguities which are called stochastic ambiguities. In this case, the question is like the inference, or what do we understand from the way the people say. Like just now I gave an example of the today's temperature is hot. So some people may interpret the temperature as above 30, but there are some people for whom the heat tolerance is low, so they might infer that as greater than 25 or something. So it depends on the person and the perception of the fact that I am saying. So yeah, like another example. So if I give an example like tall, okay. So what is tall? Someone above 6 feet is tall. Nice. So what is very tall, if I say? So someone above 6.5, And what is not tall? Someone below 6.5. But then there is the opposite word of tall, that is short, right? So are not tall and short similar or are the same, or what is that? So we have to define something else. Like the idea of being tall is not enough to express all our feelings or the rigorousness about the height of a person, right? So like I gave an example of not tall is equivalent to short, or is not quite tall equivalent to short. So for these sentences we can try the negation. Like if we assume this is true, not quite tall is short, so we can just think that what is the negation of the sentence. So this is basically quite tall and this is not short, right? So quite tall is not equal to not short because by our convention. So even this is not true, but this seems to be true, because even if this is not true, but this seems to be true. That is what it is. So we have to include some mathematical definitions here. So there was a mathematician, Lotfi Zadeh. He was from US Berkeley, and he gave a paper in 1965, and he defined the concept of membership. So like he says like the element. Look, so when we define a set, we have like a set of 2, 4, 6, 8. So now we ask the question: does 2 belong to the set or not? And we get the answer is yes, it belongs to a set. But in this question, like the budget of our gift, we had the budget from 0 to 200. But if we ask that does 210 belong to the set, so we don't get the answer as does it belong or does it not belong. We do not get a binary answer. We get like it does belong to the set, but under certain conditions. So we define membership like the 210 belongs to a set with a membership of say something like 0.8. I mean, okay, so the budget was 0 to 200, right? So if we ask that does 200 belong to the set? Obviously yes. So it has a membership of 1, but 210, 0.8, 215, maybe 0.6 or something like that. So the membership is a function which is this is for the crisp sets. The membership is defined as 0 or 1. 0 when the element doesn't belong to the set, and 1 when the element does belong to the set. But for fuzzy case, we generalize. Nice, yeah. So fuzzy case, we generalize it from a value from 0 to 1, both included. So like I gave the example, 200 belongs to the set, but 210 so 200 has a membership of 1, but 210 has a membership of 0.8. So there are some the differentiation between crisp sets. So it has a binary membership and it can have any value between 0 and 1. And like the differential is we can use operations like and, or, not. But here we have different operations and all. So example of crisp is a people taller than 6 feet. That is a well-defined set, because so like if given a person, I can classify that person as being taller than 6 feet or not, and then I can put him in the set or I can take him out of the set. But if I give an example of tall people, that is not well defined, right? So it is not a set, like not a crisp set, but it is a fuzzy set. Like if I define a membership and all, I can make it a fuzzy set. So yeah, the set A is about 10 feet. So 10 belongs to the A. So what about 8, 9, 11 or 12? It is the set, make sure the set is defined as about 10 feet and not exactly 10 feet. So I can define like 9 or 11 have 0.9 membership, because again, so if given 10, if I draw a number line, this is 10 and this should be 9, this should be 11, this should be 12, this should be 8. So given about conception is we can include a neighborhood of 10. So like 9 and 10, 9 and 11 have the same distance from 10. So just by intuition we are giving them the same membership values. So I just gave them randomly. They have 0.9 membership, and 8, 12 has 0.7 membership, 7 has 0.5 membership, like that. Now you will say that, okay, what about 2? So given the set about 10 feet, we cannot include 2, right? Because 2 is like very less. But then some will question that, okay, so we can include 2, it can have 0.0001 membership, something like that. So we cannot leave the membership function as like we are defining in some cases and we are not defining in some cases. If we have to define the membership function, to define it for all the numbers present. So here I defined the set. I defined the set as so this is how fuzzy set is being represented. So like 10 has a membership of 1, 9 0.9, 11 0.9, and like this. But defining a set like this means all the other members, they have the membership value as 0, or in other sense they do not belong to the set. This is how I define the set. Now again I included 9, right? So what about the other values like 9.5? 9.5 is also about 10, right? But then we cannot take the membership function from the discrete real line or the integer set. We have to take it as a continuous function. So I defined a continuous function from a to 0,1, and we took a as from 7 to 13 because we have to take a neighborhood, and for other points again we will decide membership as 0. So the membership function will look like this. At 10 it is 1, and it decreases linearly till 7, decreases linearly till 13, and then it is 0 at all the other points. So you can find the equations, the linear equations, and that is how it is defined. So now given fuzzy sets, we can do certain operations like union, intersection, complement. We can also define subsethood. We'll come here. So like how do we do that? So for this we need a bit of revision of the crisp sets. So we took a set, say 1 to 6, that is the universal set, and we took a subset of that, which is 2, 4, 5. So we know the complement of this set is 1, 3, 6, right? Because all the elements which are not present here. But then let's use like define the complement using the membership function. So the membership function of 1 here was here it was 0 because 1 doesn't belong to the set, and in this case it is 1, a complement. Similarly 2 was 1, and in this case it is 0, the complement case. So if you think of it, if we take this as a binary operation, it is not a, and if you think of it a bit more, so we can assign a function like 1 minus I am defining the membership of the complement function as 1 minus the membership of the crisp set function, and this is a possible definition of the complement. But then we can also generalize it, and we have some properties which it should follow. So like the properties are obviously because if you define a function for a fuzzy set, it is a generalization of the crisp set. So the properties which are followed by the crisp set should be followed in the fuzzy set, right? So this property should be followed, and one more monotonicity property comes that if so A and B are basically the membership of okay, I didn't define B. B is the membership of any other Y in capital A. So if the membership of X is less than the membership of Y in A, then in A complement, the membership of X should be greater than the membership of Y. Right? Because in a case of fuzzy sets, we won't get 0 and 1. We have all the numbers from 0 and 1, right? So we can have numbers like 0. Okay, so like example, so I take mu x is 0.5 and mu a1 is 0.6. So we have the membership of x as greater than membership, less than membership of y, and in A complement, this should be greater than mu1. So this is some modern. These are essential properties. Now some desired properties are obviously that it should be continuous, and that it should be involutive. So what do you mean by involutive? So like okay, so like if I take the membership of x in A, then I find out the membership of x in A complement. With the same operation, I can find the membership of x in A complement, which is basically A, and that should be same as this. Like what I mean is, so say let the membership be defined as A, and then we have some function C which takes the membership to the complement of A. Then I apply C again and it takes the complement of A, and it will give me back A, which is the membership of the member X in capital A. Now I gave a note, the properties are not independent, and we will see them later. Like sometimes they don't all hold together. Like we have to sacrifice some of the desired properties to gain other properties which will form a triplet, and we will see them later. So there are certain theorems. These can be proved. I didn't include the proof because it would be long. So okay, equilibrium point, right? Yeah, so what do you find as equilibrium point? Equilibrium point is basically when, so how do I define it? Given, we know about IVT, right? So given a function from 0 to 1, an equilibrium point is when you have it as a point map to a certain point. Like this is easily proven. The complementation is almost 1 because it is continuous. So also it is bijective. So at one point of time it has to intersect with the line that fx equal to x, because after all it maps 0 at 1 and 1 at 0. So at one point of time it must intersect with this line, which is the main idea of IVT. That is how we prove it. So one equilibrium. Now given there are many complementation functions, we use the standard complementation function as 1 minus mu f x. We can see it satisfies for the crystal that 1 minus 1 is 0 and 1 minus 0 is 1. Apparently this also works for all the other desired functions here. So these two are satisfied because it is decreasing from 1 minus mu f x. We just take the minus sign and the monotonicity changes. It is continuous and it is also involutive because 1 minus the whole thing just gives us back mu x. There are other complementation functions, and like if I give an example for this, this is A, and I am representing the set as this, like 2 is a member of the set and 0.5 is a membership function of A. So given the standard complement, just as I said earlier, so if the elements which are not included in A, they have the membership as 0, So when I take 1 minus it, so they will have a membership function of 1. Like 1 is not included here, so 1 will have a membership function of 1. Then 2 has 0.5, 3, 1, 4, 1, 5, 0.8, and 6 has 0. So it is not included in A complement. So let us move to union and intersection. And if you heard the previous talk of Avyakta, he said that every function from union can be made into an intersection function just by taking its inverse. So I will be covering just the union functions, and we can easily guess the intersection functions. So I took an example here again, like 2, 4, 6, 7, and B has 1, 3, 6, 7. And if we take the union, it gives us 1, 2, 3, 4, 6, 7. So again, we have to try to represent this using membership functions because we are generalizing this. So given one, these are the 4 cases, right? It might have 0 or 1 because this is a crisp set. And if we see clearly, this follows OR condition and this follows an AND condition. So again, we're representing it in terms of all real numbers. We cannot take just the binary values. All real numbers between 0 and 1. We can take this one, if you see closely, this as a maximum function of this and this, and this one as a minimum function of this and this. So does it hold for all the fuzzy cases? So we will see the desired properties, the essential properties are these. So given a union function denoted as U, it takes two membership values of perhaps x in A and x in B, and it sees a membership value of x in A union B. So let's see. So now we take the union, right? So if it has a membership of A in one of the sets, say A, and it has a membership of 0 in one of the sets, so we will say in the union it has a membership of A, because union we take the in some sense we join both the sets. So if a value has a membership of A in A, then in A union B it will also have a membership of monotonicity. So say there are two cases. In B it has a membership of B, and in set C it has a membership of C, D. If I take C, so obviously the membership will be more in A union B as compared to A union C if B is greater than C. Membership. This makes sense. Commutativity, A union B and B union A are commutative. Associativity, this is also clear. And we have some desired properties, which is again, it is continuous, and so this one. So say there exists an element X, and the membership of X in set A is A, and the membership of X in set B is also A. So by intuition we can say in A union B the membership of X should be greater than equal to. It cannot be less than A when the membership of X in both the sets are A. It has to be at least greater than or if not equal to A.
So what do you mean when you say mu A union B X is u of A? U is a function from 0, 1 plus 0, 1 to
0, 1.
but A is a element in 0, 1.
What?
I think it will be equal to B.
Oh, sorry. It should be A comma B, right?
No, but there is no B, right?
No, No, so B, okay, I defined, I took one set here, but when there is a set B, and I have to take the membership of like X in B as small b, and then I can take, basically I wrote it wrong, it should be something like this. I should define membership of X as small b, and then in A union B of X, I can write U of A comma B. This should be there. Sorry. So given these properties, we have, okay, so we have extra properties. We have this idempotency. So we know what idempotency is, and like I gave the property, right, U of A comma A, it should be greater than equal to A. So in this case, we know idempotency as f of A comma A is equal to A. So in this case, this is called super idempotent, and in the intersection case, this will be less, because think again. So I have a okay. So I have a set A, and mu of X in A is A, and mu of X in B is A. So the mu of X in A intersection B, it cannot be greater than A. So it is not greater than A, which means that it is less than equal to A. Right, that is called sub-idempotency. And okay, so we can also take the inverse of all the properties here. So like this one will still hold, U is continuous. This one will change. The signs will change. We can take the inverses and we can see that they will satisfy. Yeah, so these functions that I declared earlier, the max of A and B and the min of A and B as the intersection function and the max as the union function, they are the only idempotent functions satisfying all the previous conditions. This is a theorem, there is a proof. Idempotent means they have them equal, they don't even have less than equal to, because obviously if A and A, the minimum would be A and the maximum would also be A. That is how the idempotency holds. There are different other functions, which is the algebraic sum and the bounded sum, or the drastic property, which is this. Now, as I told again, all the previous properties don't satisfy given we have other conditions, like say for example, given this one, the drastic, it doesn't follow the continuous property, but it is defined for all the values from 0 to 1 cross 0 to 1, so it doesn't matter.
What is the reason for having like different definitions for unions and intersections?
Okay, so in all the cases, like in all the cases they don't hold, like there are some properties, these are called T norms and T conorms, right? So what we actually try to do is that we try to form triplets, and the triplets, like one function of the complement, one function of the union and one function of the intersection, and then we try the triplet to hold some properties. So now there is a set of like all the good triplets, and then there are some useful triplets which help us in other factors, like so you know the application of fuzzy, right? The application of fuzzy are in different places. So like we have estimation, we have clustering, we have regressions, and so in all the cases the same definitions don't work. We have to tweak the definitions to include some other properties sometimes, and we have to exclude some properties sometimes. So we have different definitions which will help us to do the work. So I give an example here, which you can see. So I took a universal set and I took A and B given the memberships. So this is a union which takes the maximum value, and this is the intersection. So again, if you see if the element, the fuzzy, so if we try to construct a crisp set using the fuzzy set, so just remove the memberships, have 1, 2, 4, 6, and 1, 3, 5, 6, which is the previous example, and we see the numbers 1, 2, 3, 4, 5, 6 as included. So this is how we can define the union and the intersection. Now there are other properties we satisfy. Basically, if I generalize this, so we have cardinality, we have the De Morgan's law. This you can verify given the functions, and we can define subsethood. So this is a bit hard to define in case of normal sets if we take the other functions, but this can also be defined, and we can also define something a bit more general, which is the degree of subsethood. If this is this. So given A and B, we always can't say that X is a subset, A is a subset of B, but we can say that A has a degree of subsethood, like A has a degree of 0.7 subsethood in B. So that is how we can define. Like this is also a fuzzy definition in case of subset. Now these properties like excluded middle, so A union A complement is a whole universal set, which is not true, because okay, so but if you take like the fuzzy set here, yeah, so the A union A complement. Now in this case this holds, but then if we take like 2 and okay, so by the way A and A union, and this should be like this, like A disjoint union A complement, but then there are members which exist in both the sets, so we cannot take the disjoint union, and then this doesn't hold. Like to say more clearly is that A intersection A complement is not phi. We have some people like this also has a degree of subsethood in this, because this element is belongs to both the sets. Yeah, so this is where I defined that these triplets, so this is called the standard triplet, the maximum union function, the minimum intersection function, and the 1 minus this as a complement function. This forms a triplet. So these union functions are called the T norms, and the intersection function are called the T conorms, and the taking all of them, they satisfy some property. Like there is a theorem which says that okay, so like to answer your question, there is a theorem which says that the algebraic sum property, this takes in some sub-idempotent values, and I think they map it to some other values, which I mean there are some properties which I don't remember the theorem exactly, but then if I take the whole algebraic sum conorm, then it forms a different thing, like from standard conorm. Okay, so now I can try defining some fuzzy numbers. Like I defined fuzzy sets, so for operations we need fuzzy numbers, and I can still define. So what are fuzzy numbers? So fuzzy numbers are basically fuzzy sets which follow some property. So again you have to keep in mind that fuzzy numbers are generalization of real numbers, just numbers. So all the numbers which we know, like these 46 or 254, they should be fuzzy numbers, as well as the numbers like near 100 or about 20, they should also be fuzzy numbers. So we have to define some properties which take care of all of them, and including these new numbers. So okay, so given the fuzzy set, the membership function, to define the properties we need some definitions. First of all, which is normality, and normality is that there exists an element in A which has the membership as 1. I mean, it belongs to the crisp set of A. That is what I mean. So like in this set A, the number 1 has a membership value of 1. So we can say that A is normal because there exists an element. And then there is something called the support. The support is that like they have in the crisp set they have memberships as greater than 0. Like there should be some numbers which should have a membership value greater than 0, excluding this number in this case, because if this case is normal, then obviously the support should be greater than 0. But yeah, excluding these numbers. And there's a third case which is okay, alpha cuts. How do I define alpha cuts? So yeah, so this is a fuzzy set, right? And I define alpha to be a value from 0 to 1 because okay, B is normal, so this has a membership of 1, and I define an alpha, and I basically cut the region, and I can see all these numbers like from A alpha to B alpha, they have the membership values greater than alpha. So like this is basically kind of truncating. I take all the numbers in the set which has membership functions, membership values greater than alpha, and the property is that
Okay, did I write the property here?
remember, okay, so in the fuzzy numbers the property is that all the alpha cuts should be closed. Now okay, clarifying here. So a fuzzy number should have all these three properties, which is it should be normal, and the support of A should be bounded, which is okay, support means the elements which have the positive membership should be bounded, like there exist W1 and W2 such that the X belonging, okay, so if it is bounded, I'm writing here W1 and this is W2. So all the members between W1 and W2, they have some positive membership values, and the members which do not lie here have membership values as 0. So all the members from minus infinity to W1 and from W2 to plus infinity have membership values as 0. And all alpha cuts of A should be bounded. Okay, I said closed. This is bounded also over here. And yeah, so the first question which comes to our mind is that we cannot check all the alpha cuts of a fuzzy set, right? Because checking, like there are an infinite number of numbers between 0 and 1. Just taking the reals are not possible. So we have to arrive at a different definition. Like this is the actual rigorous definition of a fuzzy number, but then we have to take some properties of it so that we can justify this definition. So how do we do that? So we gave a form, like the other did this. So we gave a form of the fuzzy numbers, like how do they look like? So think of a real number line A and B, right? Okay. And also I take two more numbers, which is W1 and W2. So what is said here? The point is said that the membership value is 1 on some interval A to B. So now this A to B interval, this has a membership as 1. Right. Lx is a monotonically non-decreasing function in minus infinity to A. Minus and W1 should be such that Lx is equal to 0 from minus infinity to W1. So basically, if I define the membership function, which is basically a graph, so from minus infinity to W1, this should be 0. It would have been nice if I could use a different colored chalk. It's okay. This is 0. After that, this is an increasing function, non-decreasing from minus infinity to A, but since it is 0, so it will be increasing from W1 to A, which is, I can take it something like this. I have to follow the other properties too. So this is the function, and from a to b it is 1, and then there is Rx, which is a non-increasing function from b to infinity, but then we have the alpha cut, which is 0 cut, as closed. So there exists W2, after which it would be 0 till infinity. So we can say that this is a decreasing function from b to W2, and it can be something like this. So this is how a fuzzy number looks like. Now this is right continuous and this is left continuous, so we have to take care of the corner cases, and that is the definition. So now what we can do is we can take different type of fuzzy numbers, right? So we can make these lines straight, and then this is what we call as a trapezoidal fuzzy number, because it looks like a trapezoid. We can take A and B to be the same point, and then it will look like this, which is a triangular fuzzy number. Now this definition is a generalization of the fuzzy numbers and also the sets, right? So if I take a real number, okay, by the way, this theorem just comes from this definition, right? So we can show that this definition and this theorem are equivalent, and using these three. So okay, so let's cover with the proof first. Then it said that all the alpha cuts are closed. So the one cut is closed. One cut, it should be a 0. 0 it should be closed, because after this we take a line at 0 and it should be closed. And so there exists W1 and W2. After which, I mean, from the whole support will lie in this interval W1 to W2. We can say that the other numbers in the real line will have the membership as 0. And A is normal, so there exists one element from within W1 and W2, because the support is positive, which has a membership of A, right? So we just extend it, given an interval A to B, we can prove that there exists one element such that it has a membership of 1. So trying these definitions and also the rest of the hints given these lines. So if there exists a number with membership 1, and then we know that before W1 the membership was 0, so we can take a look at this function and we can say that it is non-decreasing, and for continuity we can also construct a proof, and this proof is an if and only if proof, so works both ways. But yeah, what I was saying that to get the examples of the real numbers. So take a real number A, and I took it as 5. Okay, so in this case, A, B, omega 1 or W1 or W2, all of them are same. So it is 5. So basically, I took all the 4 points and I compressed them to 1 point. So the closed interval in which the support it is normal, or the membership value is 1, is basically 5, 5 closed, and it contains one element 5, and from which the support is positive, it has 5, 5, because only one number will support positive. All the other numbers has support negative, or has membership function as 0. So we can define Lx and Rx as 0 from minus infinity to 5 open and 5 to infinity open, and both of them are constant functions, so they are non-decreasing and non-increasing and continuous, because as they continuous they are both left and right continuous, and the other properties also hold. What about a real interval, say a comma b? So in this case, still we don't have increasing or decreasing function, right? As I showed the example of the trapezoidal fuzzy number. We had an interval b to w2 or w1 to a, which had a. Okay, so the case that is the reason why we say non-decreasing instead of increasing, because it might be constant or something. So like in this case, this was strictly increasing because this w1 to a, this set was not 5, but in this case this set has nothing, right? So there is no function, but the a to b we have different, like we have increased this space here and this space here, but we have an interval a to b, which is the real interval, in which case all the members are present in the set, all the members have membership function as 1, and all the other members are not present, so they have a membership function of 0. So this is how we represent an interval as a fuzzy number. But then again, we can compress a and b and keep the distance between omega w1 and w2, so which will give us a triangular fuzzy number, which I showed in the example. And also we have a trapezoidal fuzzy number, which is generalized case. Now these are some standard examples. There exists also different types of fuzzy numbers. So like I can have a combination of a triangular one and a trapezoidal one, but then after all they will have to follow the theorem and the conditions of the Lx and Rx. So now given fuzzy numbers we can perform arithmetic, so they follow same as the interval arithmetics. So these are the interval ones. So if we take the inverse, I take p by a to a by a, given that 0 doesn't belong to a comma b, and if I can add them interval wise. Now this might sound a bit easy to like see, but then if we take the intervals here, like if we take a real interval and then we try to actually add them. So what do we mean by adding? So we add all the elements and the membership functions, and this can actually be written as a membership function. So I can write this as mu x such that from it is 1 from 5 to 10, and it is 0 from minus infinity to 5, the union 10 to infinity. And then I take another numbers and then I add. So 1 and 1 adds, 0 and 0 adds, and if some other numbers are present with some other fuzzy cases, they will remain as they are because they are basically added to the 0 1. They cannot be added to the 1 because 1 is the maximum case. So this is how we obtain these results, but in this case they are intervals. Even if we work with fuzzy numbers or fuzzy intervals, we have the same results because they occur. Now we can generalize them, generalize the addition to some extent, but then we don't need that here. It's like this. The fuzzy arithmetic works similarly after all intervals are fuzzy numbers. You can generalize the definition to fuzzy relations, and for this we need to revise the relation. So relation represents association or lack of it between elements of two sets. This is a very, I don't know, a bad definition, but then the difference between relations and functions that there can be one to many relations, but there cannot be one to many functions, and mathematically it is basically a subset of the Cartesian product of sets. So given an example, if I take an example, okay, I did take an example, it's okay. So I need to firstly represent the relation so that I can generalize it in fuzzy ways. So there are various methods of representing a relation. Yeah.
What would the Cartesian product look like in terms of results?
Yeah, so firstly, I am writing this in terms of crisp sets so that I can generalize it.
Okay.
In terms of fuzzy sets also, so Cartesian, okay, so what is the Cartesian product? We will take the crisp set. So and we will include all the members as here and here in the fuzzy sets, and then we can assign some membership values to other to confirm the relation, right? So while working with relations, we first take the crisp set of the fuzzy set, like you understand, so we just take out the membership values, and then we can give some membership values to the relation, so that is actually satisfies as a relation. That is what we are assigning, trying to do. So firstly we have to take a representation. One of them is, okay, so one of the most common way of representing a relation is take a domain and codomain and we map the elements like this. But then I can also go like this. So, but then there is no notion or way to express the membership values here. So I am not taking this representation. I will be taking a different one which has a graph. So basically I take the points of the set A here and I take the points of set B here, and then I define the different points. I define, okay, so did I give an animation? Okay, yeah, so I take the X as a set of teachers and Y represents set of subjects taken up by them. So R represents the relation. So let's say teacher X1 takes a subject Y1 and Y2, X2 takes a subject Y3, Y4 and so on. So how do we represent it? We take a graph and we write as Y1, Y2, Y3, Y4, and we just highlight those points which are included in the relation. So if I take the whole Cartesian product, all the points, all the lattice points, what to say, will be included, which is these are the points. So now if I take the point R23, it just means the teacher X2 taking the subject Y3. Now I can assign values. So I can assign 1 or 0, representing that it does belong to the relation or it doesn't belong to the relation. So now in this case the domain is this and the range is the x-axis. And so when I assign the values to the R, I am assigning it 1 or 0, right? This is in the case of crisp sets. So now when I will do that in case of fuzzy sets, I will not assign it as 1 or 0. I will assign it as a random value, not a random value, but a value from 0 to 1 closed. That is how I extend the definition. So I took a set of all cities and I took a fuzzy relation of the concept of distance, right? So if I have to plot, this represents the cities. I took the initials of the cities because it's too big. So I took the initials of the cities and I plotted a relation from x to x. So it should be basically like if I take every city to itself, like from A to A, the distance is 0, right? And I take very far away cities. So like if I take K is Kolkata and A is Ahmedabad. So Ahmedabad to Kolkata distance is very large in comparison to this set. So I take it as 1. Now this way we can assign, like if I have a 0 and 1, then I can compare the other values and I can assign some fuzzy real. This is not exact, so this is an approximate. So I can assign the values and I will get the fuzzy relation as it is, looks like this. So now these elements A, C, C, D, D, they do not belong to the set, but the other elements belong to the set R with the membership values, those are as represented. Did you get it? Yes. So in this case we take okay, so again now if asked the membership of X, say in the domain of R, so it will, we can take that again as maximum of this row, like Y present in Y. So Y is this case and given X, okay, so if this is given, in this case it doesn't matter because we took the same set x, and so the maximum in this case will be the maximum in this case because they are in fact symmetric. But in given a general case, if I have to represent the membership of A in the domain, so we take the maximum of this row, and that would be 1. So the membership of A in the domain set of R is 1. So if we take something example which is not 1, like H has a membership of 0.8. That is how it works. Because so why does it work? Like if I have the membership of like in a relation R, so I have all the different memberships, right? So given the domain, I took a crisp set as the actual domain, but if I have to represent as fuzzy set, so I will take the membership that it does belong to the domain, but in what is membership? Like in how much sense does it belong? So we can take the maximum sense that it belongs this much to the domain, and that is the maximum of all the relations present here.
Yeah, so in the case of say we are taking like a relation from a fuzzy set x to a fuzzy set y, so for any particular element, is there any upper bound? For example, in the crisp sets which give us fuzzy relations, we had a range of like 0 to 1 closed. But in the case of say relation from a fuzzy set to a fuzzy set, would that be affected or is it still?
It is still 0 to 1, right? Because after all, we are taking the we are generalizing this from a crisp set,
Yes.
and the extremum case in the crisp set is doesn't belong to the relation, so it is 0. So we cannot take it below 0, or we cannot take it above 1 for the same matter, because it does belong to the relation in the full sense. What is membership, right? That is eventually that is even the relation set is a fuzzy set, so it has the same membership values as defined in the fuzzy sets, which is 0 to 1.
No, like what I mean to ask is, see, A comma B belongs to the relation. So, like, won't the upper bounds or lower bounds be affected by the fact of like by the
But it is a
memberships
member of a set, right?
Yes.
Yeah. So it is a fuzzy set, and it has a membership from 0 to 1.
That it does. I'm asking like for the particular element of A to B, A comma B, sorry, where A belongs to X and B belongs to Y and Y. So in that case, do the individual memberships of A and B in the respective sets change the range of the membership function, for the?
No. In case of relations, we take if we take a relation R from X to Y, where the set R is a fuzzy set. These X and Y are crisp sets; they are not fuzzy sets.
Okay.
So the question of these membership affecting them doesn't come because they all have membership as 1 or 0.
Okay.
We define the membership after we form the relation of the domain and codomain, not of the original sets. Okay, so this is how fuzzy relation works. We can extend the concept to fuzzy logic, and this is in fact where the applications start to show up. And so, like if I ask a question, is it cold? I have two, in the Boolean logic I have two values, which is yes or no, 1 or 0. But if I take is it cold in fuzzy logic, I can have very cold, which is 0.9. I can have little cold, 0.25, or I can have very less cold, which is 0.1. And that is how we basically in case of neural networks, if I take the Boolean logic, so previously the Boolean logic was taken, so it branched out, it obviously branched out, but in case of fuzzy logic, it branched a lot more. So in case of advanced systems like say the AI bots like ChatGPT or DeepSeek, they implement the fuzzy logic as a neural network connections because it provides a lot much more scope for understanding humans or for the natural language processing in general. So yeah, I also gave a graph here. So these three are three fuzzy sets. Like this has the value. So like the temperature, I took it I think in any scale. So if it is less than 0, it is obviously cold, right? But then from 0 to say 0.5, it decreases. So if I ask, is it cold in 0.5? You can say no, it's not that cold, it's a bit less cold. And the warm graph, it increases. So if I ask at about, this is actually I think a whole graph of temperature. So if I ask at 5, so it is more warm than cold. It is not fully warm, it is not fully cold, but it is more warm than it is cold. If I ask an average person, it would be like, do you feel cold or do you feel hot? He might not answer. But if I ask that, is the warmness more or is the coldness more, degree of warmness or coldness, then eventually he reaches to the answer that the degree of warmness is more than the degree of coldness. Similarly, it is warm, right? Warm lies in between. It's not hot, but then the warm, it goes from say from 5 to 10, it is warm. But then the warm results saying warm decreases and the result saying hot increases. Say from about 15, hot starts from 15. So if I ask at about 12, so people is like, okay, it's not warm, but it's also not hot. But after that, as the temperature increases slightly or it goes on increasing, people say it's hot. So the membership of hot becomes 1 and the warm decreases. That is how we can represent it as a graph. So, okay, so this has a generalized concept, fuzzy graphs. Fuzzy graphs, okay, so this is representation. So we know what normal graphs are, right? So we know normal graphs is basically extension of relation. We have the vertex set and then we take a relation E from the V to V such that it is 1 or 0. Either the edge exists or it doesn't exist. So now I define some other functions, which is sigma, which goes from V to 0, 1, and mu, which goes from edge set to 0, 1, which represents the fuzzy membership of the edges, and this represents the fuzzy membership of the vertices. So now there are some conditions, and if I take an example, it looks like this. So there are the points A, B, C, B, and then I join the vertices to form edges, but the edges have membership. Now one condition is that the membership of the edge should be less than the minimum of the membership of the vertices. So like for all the vertices. So like in this case, it has 0.5 and 0.9. So the edge membership must be less than equal to the 0.5, which is the minimum of 0.5, 0.5. So now there is a book on fuzzy graphs. I took that as reference. You can read that for more information. This is how the example. So this is how it looks like, and this is how all the membership functions are represented. So given the set V, we can write it as V sigma. So like A, 0.5, B, 0.9, and like this. Now this concept can be further generalized to fuzzy topology, and there are other variants of it. We also have fuzzy logic, as in fuzzy quantum theory or something, but then they are still in development. We just work with that. Should I cover this topology? I mean, if you know what a normal topology looks like, we basically, what we do is we add membership function to all the, like, to everything that we had the 0 or 1, as in this set. We just generalize it to this. And we try to satisfy certain properties. Now this fuzzy topology, this part is like, this was mentioned in a research paper of a master's student, but then it was extended further obviously, but then it was first stated here. So now you can understand that this is a developing subject. So this can develop to many fields, and it might have applications, it might not have applications as we desired, but then it is being used recently. So
What is the topology? I don't see the topology. I don't see the open set here.
I gave the pair as X as the fuzzy topological space.
No, but what are the open sets in the topology?
Oh, okay. So given I didn't define the open sets here. Okay, so if I define a set here,
X
like
is a very arbitrary set.
let's take a space A units. Really makes the definitions of
I don't mind. We can discuss that.
I didn't define it, sorry. I made this a definition. Here. This was what it was defined as. Yeah, so the oh, I didn't define A, right? A is the set. I think so.
Yeah, A is an arbitrary set.
A is an arbitrary set.
Yeah, but
Which-
I need an open set. Right? So are you saying all the sets are open?
To some degree.
No, it's probably not true. I didn't much into it, but A is an open set. Probably. Yeah, A is an open set.
No, no. I mean, okay, A's open set is fine, but what are the open sets? So do you have the open sets definition in the beginning itself?
I didn't look into it, but we can define.
So is every set open to some degree?
Yeah, that is true because I mean, so how do I define it? I don't have the formal definition here, but yeah, if we are considering this as fuzzy, so then A might be a set and we have a degree of openness. I don't know exactly. I can't tell you about it. So I will look into the matter. I just gave the definition. I didn't cover it. I think there is I even I believe that there is a degree of openness. Yeah, we didn't define that here. Yeah, I gave an application which is fuzzy clustering. So if you know the normal clustering, which is basically providing it into different clusters, like I I group substances, which is normally used in machine learning. If I have say different objects and I have the machine to sort them out, the machine will sort both of them in two different categories, right? But then if I have an object like this, so it doesn't understand where do we sort it, right? So we can assign the fuzzy membership of the sets in which we are clustering them. So then it has a degree of say 0.7 or 8, and this has a different degree. Then this can be sorted because this also has some degree of this. Okay, so this is A and this is B. So if this shows some characteristic of A, say 0.7, and of B, say 0.3, and this has a degree say of acceptance 0.5, then obviously this goes into A. But in case of normal clustering, that is not done so. So machines normally use fuzzy clustering, but we don't see that. This is the example. And then there are different applications. These are the research directions here, which are the fuzzy logic and the granulation, and also it is used in cybersecurity and IoT, which is the same. And this is the book I was talking about, Fuzzy Graph Theory. I should have also referenced that paper, from which I took the fuzzy topology. But yeah, I will see into it.
Okay, I have a doubt. So in the fuzzy graph, so isn't that basically like the X set in this case? It is basically a relation from B to B, but with instead of it lying from 0 to 1, it goes from 0 to the minimum of the 2 points.
Yeah.
So we could consider it as that, right?
Yeah, it is a relation.
Yes, but like you defined fuzzy relation to be from crisp set to crisp set. That's what I was asking.
No. Yeah, this is a relation from V to V.
But V
This
is
view is from V to V from 0 to 1.
yes.
Yeah, but it has an additional condition that it should be less than the minimum of these two.
Yes, I'm aware. That is why, right? Because V is itself a fuzzy set.
No, V is a normal set. I define another function as sigma, which has the fuzzy relation mapping. Not relation mapping, the fuzzy mapping here. The V is defined as a actual set, like the real set of all the vertices.
Okay.
The graph is defined as V, sigma, and mu. The sigma contains all the membership functions of the V, and mu contains all the membership functions of all the edges.
So, anybody has any questions? If not, then let's speak.